Here's what's going to happen today. Oh, if you think, we're going to learn more about the speed of sound and air. Then we're going to talk about sound intensity, and then what we humans hear as loudness, which we use decibels for. First, speed of sound. Okay. If temperature of air is raised, speed of sound increases or decreases. You must decide. Please think about this for a second. If I raise the temperature of the air, is that going to make the speed of sound increase or decrease? It's going to go up or go down? Okay, you guys ready to vote? How many people here say the speed of sound increases? Okay, many of you. How many people say the speed of sound decreases? One of you. Okay, Giancarlo, why do you say that the speed of sound would decrease?
I was thinking because I remember that in water, the particles are closer together, so the sound goes faster. If the temperature of air is increased, the molecules are farther apart, so it goes slower.
Great, that's incredibly logical. Good for you, that's totally true. Tell me, why would someone say that the speed of sound would increase? Yes, Gavin?
Well, I was thinking if the particles are moving faster, then they're coming in contact with each other more often, so the speed of sound will increase.
Wow, what you said is totally correct. That's true also. So how can we tell which is more powerful? How do we tell which is more influential? I guess just testing, you know? But are you guys okay if the particles are farther apart? Remember the thing I told you about people standing in a circle and squeezing each other's hands? And then if the people, instead of holding hands, are separated by 2 meters, so you know if they're separated by 2 meters, I've got to do a couple of steps before I can squeeze their hand. That's going to make the disturbance propagate more slowly. But what happens if I'm Kid Flash? What happens if I can get from here to there really, really fast and then squeeze hand? That means the disturbance will go faster, at least faster than you would think. Well, it turns out that these guys win. The speed does indeed increase. It increases because the particles are moving faster. I got to tell you, last period, when the students were talking about what happens, they were talking about the wave bouncing off of the particles. But I want to remind you, this sound wave isn't bouncing off the particles. That makes it seem like the sound wave is something apart from the medium. It isn't. The sound wave is the medium itself. The wave isn't bouncing off the particles themselves are doing the bouncing. The only way a wave can propagate is if this molecule rams into this one, and this one rams into this one, so that this one rams into this one, and this one rams into this one, and this one rams into this one. You see what I mean? Like, so the way a sound wave propagates is through molecular collisions. And so it turns out if the molecules are moving faster, they tend to have those collisions happen more quickly. This molecule can get from here to there to have this collision more quickly if his temperature is high, which means he's moving fast. And so the speed of the disturbance increases. Okay? Here's another question. You talk or sing, and what happens is you've got a bunch of nitrogen molecules in your lungs, and then you talk, and those nitrogen molecules are set into vibration, set into that sort of thing. So here's my nitrogen molecules that I'm using to speak, that the sound is propagating through. Okay? There's my nitrogen molecules. How many people here have breathed in a bunch of helium and then spoken? Okay, it's great fun. What happens to your voice?
Gets higher.
goes higher, goes way higher, okay? So you breathe in a bunch of helium atoms.
It's really light.
Okay. Here's my helium atoms. Someone tell me why. Why does your voice have a much higher frequency when you talk using helium atoms rather than nitrogen molecules? Yes, Gavin?
Helium atoms have a lower molecular weight, so they move faster, and so your sound is moving faster when you talk, so you talk higher.
Okay. You guys okay with that? He's going, these guys have a lower molecular weight. They're lighter, if you will, and so they move faster. And so your frequency is higher. First of all, what equation tells me that if they move faster, my frequency is going to be higher? What equation tells me that? Do we have an equation that relates speed of the wave with the frequency of the wave? Fatima, you're nodding your head. Which equation is that? Hey, the most important equation that we've learned in this chapter. Okay? Now, one thing I want to tell you, just as a guitar string, if the length of a guitar string is set, then the wavelength is not going to change. The wavelength of the vibrating guitar string is determined by the length of the string. And if you don't change the length of the string, you're not going to change the wavelength. Well, it's the same thing with your vocal cords. Your vocal cords have a particular length, and that's not going to change. So yeah, you raise the velocity, you raise the frequency. Beautiful. But let me ask you a question. Why is it that lighter atoms move faster than really heavy molecules? Why does that even occur? What's that?
There's some sort of the diffusion equation.
Okay, no, actually something easier. Let me just tell you, both of these are at the same temperature. Both the nitrogen that you speak with and the helium that you speak with are at the same temperature. So tell me, what is temperature measured?
Average kinetic.
Yeah, beautiful. Average kinetic energy. So these guys are going to both have the same average kinetic energy. So tell me more. Why do those guys move faster? How would you answer this on an AP exam? Yes, Fatima?
So since they have the same kinetic energy,
Yes.
but the nitrogen atoms have greater mass, their velocity will be lower so that it equals the mass times velocity of the
Beautiful. And by the way, you would use 1/2 mv squared, not momentum. But yeah, right? The kinetic energies have to be the same, and the formula for kinetic energy is 1/2 mv squared. Well, for the nitrogen, big M, small v. For the helium, small m, big V, right? And so just be prepared to answer a question like that on the AP exam. Those atoms move faster because they have the same average kinetic energy, because they have the same temperature, but because kinetic energy is 1/2 mv squared, small mass, big velocity, big mass, small velocity. Okay, great. Hey, that's all I want to say about that. Let's talk about sound intensity. Sound intensity, which our book calls capital I. We need some way to measure how much energy sound has. And so we use this quantity, sound intensity, to measure how much energy the sound has. Sound intensity is power over area. Power has the units of watts, and area has the units of square meters. Why do we use power rather than energy? Well, I'll tell you, it's because of the nature of sound. Who was it who shoved me the other day? What girl was it who shoved me? Was he, okay, Amani? So when Amani shoved me, I could measure how much energy she imparted to me because her shove was a single occurrence. She shoved me, she exerted a force over a distance, I gained energy, okay? But sound doesn't tend to be like that. Sound usually just goes on and on for lots and lots of minutes, okay? And so rather than measuring the energy of the sound, it's actually more convenient to measure the power, the joules per second, and then you can just multiply by the number of seconds to get how much energy the sound had, okay? Because like I said, sound tends to be, over an extended period of time. And then area, this sound, these air disturbances, these waves in the air, these compression and rarefaction waves in the air are hitting an area. And the larger the area, just like a sail on a boat, the larger the area, the more energy that sound's going to impart. You see, if that sound is coming in, if you've got this huge big wave of sound, the more area that sound hits, the more energy you're going to get. So that's why we tend to do a sound in terms of watts per square meter, power per area. Okay? Hey, let me show you the relationship between sound and how far away you are from the sound. Let's say I had some speaker, and the speaker was putting out sound in all directions. And I wanted to catch all of the power, the total power being given by the speaker in all directions. Well, one way to do that would be just to put a sphere around it. Okay, just put this sphere around it, and the sphere will catch all of the sound. And now I can get what the surface area of the sphere is. I can take the amount of power that the speaker is putting out, and I can measure that power maybe with the electricity going to the speaker. And I get an intensity of power over area, which in this case is going to be (4 pi r squared), where this is the radius. That's the radius of the sphere. Tell me, what if I were to double the radius of my sphere? What would happen to the sound intensity at some point on the sphere? So I've just doubled the radius of my sphere. Okay? Knowing that intensity is power over 4 pi r squared, I've just doubled the radius of my sphere. This radius from there to there is 2r. Now, what's happened to the intensity, the sound intensity? What's that?
It's going to be cut by 1/4.
Yeah, it's going to be cut to 1/4 its previous value, right? Because now the new intensity is going to be the power that speaker is putting out, which isn't changed, divided by 4 pi times 2r squared, which is the same as 1/4 times power over 4 pi r squared. You see? To put it in a different way, suppose I had a particular area on this sphere, okay? And I wanted to know how much energy this area on the sphere was getting. Well, I would just take the intensity, multiply it by the amount of time, by the number of seconds that I care about, and I'd multiply by the area of that little patch, however many square meters that is, and that's how much energy this guy's getting. Well, if this same patch is over here, I'm going to get a lot less energy because this energy that's coming out is now being distributed over a sphere with 4 times the area. And so I'm only going to get 1/4 as much energy on that little patch. So to put it in words, sound intensity, just like gravitation, sound intensity is inversely proportional to the square of the distance. Sound intensity is inversely proportional to the square of the distance. That's all I wanted to accomplish with this, to have you see that sound intensity follows inverse square law. So let's say I'm at a concert and the speaker's really loud. I've got my daughter with me and I don't want to expose her to really loud sounds. What's the best thing I could do? What's that, DeAndre?
You get farther.
Yeah, get farther away. Because it works out really great. If I triple my distance from the speakers, by what factor am I reducing the intensity of the sound? Yeah, 1/9. That's awesome. I don't have to get that far away at all before it starts being reasonably, not that loud. All right, well, that's all I needed to say there. The last thing I want to talk about is the way we measure loudness for us human beings. And that's with decibels. Okay. Intensity level, which another synonym for that would be the loudness. How loud we human beings hear stuff. We call that beta. Let me just go here. Okay, so here we go. Here's something I want you to see about our ears. Okay. We're able to hear an incredible range of intensities. We can hear sounds as soft as a trillionth of a watt per square meter, and we can hear sounds as loud as the threshold of pain, 10 watts per square meter. That's a stupendously large range of values that we're able to hear. But the thing is, like a live rock concert, it sounds a lot louder than the threshold of hearing or rustling leaves. But I'll tell you right now, a live rock concert subjectively does not sound a trillion times louder than our threshold of hearing or rustling leaves. It sounds loud, but not that much louder. Or let me put it a different way, okay? Consider, inner city traffic, city traffic versus a car without a muffler. A car without a muffler sounds louder than normal traffic, but it doesn't sound 100 times louder to us. It just sounds incrementally louder. It's like a lot louder, but not 100 times louder. And that's because we humans, we hear logarithmically. It turns out every factor of 10 increase in intensity brings about an incremental increase in how loud we think something is. And we get this by using this formula, that the intensity level beta is equal to 10 times the common log, not the natural log, but the common log, log base 10, of the ratio of the intensity you're interested in over the reference intensity. So I naught is the reference intensity. It's what you're comparing your intensity to. And I is your intensity. So let's actually go through some of these, because now this is just a math issue. Let's say my reference intensity is the threshold of hearing. Let's say that's my I naught, threshold of hearing. Then how many decibels? Oh, by the way, I forgot to put that the units of B, the units of beta is decibels. And it's 1 L, not 2 L's. Decibels, or dBs. Well, here I got 10 times the ratio of my intensity over the reference intensity, if I'm going to use the threshold of hearing as my reference intensity, the log base 10 of 1 is 0, so this ends up being 0 decibels. How about rustling leaves? That's going to be 10 times 10 to the negative 11th over 10 to the negative 12th. 10 to the negative 11th over 10 to the negative 12th is 10. The log of 10 is 1. The beta is, log of 10 is 1. 10 times 1 is 10. I got 10 decibels. So here's my next one. I'm now going to increase by another factor of 10. How many decibels is a whisper going to be? What do you guys say? What's a whisper? Is anyone here getting 20 decibels? Nobody? Okay, let me just plug in. I got beta equals 10 times the log of 10 to the negative 10th over 10 to the negative 12th. 10 to the negative 12th over 10 to the negative 10th over 10 to the negative 12th is 10 to the second. The log of 10 to the second is 2. 2 times 10 is 20. I'd like you to see that a whisper is 100 times bigger, 100 times more intense than the threshold of hearing. But because a whisper is 100 times more intense, it ends up being only 20 decibels bigger, because every factor of 10 in intensity just adds 10 to the decibel level. So let me ask this. What if I had something with an intensity of 10 to the negative 8 watts per square meter? Remember, my reference intensity is 10 to the negative 12th. So this 10 to the negative 8th is 10 to the 4th more intense, or 10,000 times more intense. How many more decibels is that going to be? And I want to remind you, 1,000 is 10 times 10 times 10 times 10. Yes, Cole?
Is it 40 decibels?
Yeah, good for you. How'd you get that?
I just plugged it into my calculator.
Good enough. He just plugged it in his calculator. But I hope you're seeing that for every factor of 10 increase in intensity, you add 10 decibels. Since this is 10 to the 4th times more intense, it's going to be 40 more decibels, right? So this ends up being 40 decibels. Here, let me skip to this guy before I do normal conversation. Because normal conversation, you're going to do like Cole. You're just going to punch it in your calculator and get 65 decibels. But how about city traffic? This is 10 to the negative 4. This is 10 to the negative 12. So this is 10 to the 8th more intense. How many decibels is that going to be? How many people are thinking 80? Okay, good. Good, because every factor of 10 means 10 more decibels. Here, let me ask you another question, okay? I've got a quiet classroom. Let's say my quiet classroom is 42 decibels. Let's say I've got a loud classroom. That's 1,000 times the intensity, 1,000 times the sound intensity, 1,000 times the watts per square meter. Well, we're not going to hear the loud classroom as being 1,000 times louder. How many decibels is that loud classroom going to be? Let me get someone besides Cole who knows all the answers. Yes, Alejandro?
72.
How'd you get 72?
Since it's 1,000 times, that's 10 to the 30, and then when you plug it in, that's 30 more decibels, and I added it to the 46 decibels.
Great. Are you guys okay? Because it's 10 to the 3rd times more intense, I'm going to have to add 30 decibels. This is a 72 decibel classroom. That's it. That's how we hear sound. One thing I want to leave you with, I'm going to talk about tomorrow. How many people read or heard about the car bomb in Kabul that killed 1,000 people, killed 100 people? Okay, I want to ask you this question. What killed them? What's that? Yeah, the sound. Air. Air moving really, really fast, disintegrates their bodies, separates their limbs from their bodies, kills them dead. It's sound that kills them. It's the air. It's not shrapnel, it's the air. If I put a car bomb on the moon, could I kill a bunch of people?
No.
No. There's no air on the moon, and there's no people. Okay. Well, thank you very much. Bye-bye.